Hey Geometry, let's dive into volumes a little bit deeper, and specifically volumes of pyramids and cones. We've already been using the formulas for them a little bit, but today we're going to dive into where the formulas actually came from and how they're developed. So first of all, we don't have provided manipulatives, so I provided you with some pictures and sketches. What is the formula to find the area of a triangle? Well, if we look at this rectangle right here, I have base of a rectangle and height of a rectangle. So if we had area of a rectangle equals base times height, when I draw a diagonal here, I still have a height and a base, but the area of my triangle is 1/2 of a rectangle, or 1/2 base times height. That's why the formula works. Height is always at a right angle, so even if we had a parallelogram, base, height, that's the area of a parallelogram is base times height. But if we make a triangle out of it, it's still half of the parallelogram, and we have to use the measurement for height of the triangle. So it works. Formula to find the volume of a triangular prism. Well, volume, I've always learned like big B times H, where big B equals the area of the base of whatever prism you're trying to find the volume of. So if we have the volume of a triangular prism, our base is a triangle. So big B is 1/2 base of the triangle times height of the triangle times height of the prism. So this right here is area of the triangle times height of the prism. If you think of a triangular prism as just, I'll use my little highlighter thingy, a bunch of areas of bases stacked up, one right next to each other, keep on going. I mean, it would take me forever to change colors, and it's just a whole bunch of areas of the bases, whole bunch of bases stacked up, one right next to each other, the whole length of the height. Okay, we would just keep on going until we finished all the way to the end. That's sort of pretty. So that's why we would do the area of one base stacked up the whole length of the height of the prism. That's why the formula works. Things get a little bit more difficult when we talk about a cone or a pyramid. I'm going to do cone first because that's the picture that I have. This right here was a really fun animated graphic that I found. Okay, this cylinder and this cone are the exact same heights. Okay, the heights are equal. And the volume, like this right here, if this were liquid in this cone, you could pour it in and it would fill up. Like if we made it green, you could pour the liquid or the volume that is in this cone, you could pour it into 1/3 of the cylinder. So the volume of a cone is 1/3 of the volume of a cylinder. Sorry, I'm not in a pen. The volume of a cone is 1/3 the volume of a cylinder. So if I look at the volume of a cylinder, volume equals big B times H, where big B equals the area of the base, which is a circle, which is pi r². So volume equals big B times h. So volume equals pi r squared, which is the area of the base, times the height of the cylinder. So the volume of the cone is 1/3 pi r squared h, where pi r squared is big B, area of the base, which is a circle. Cool? And amazingly enough, it works the exact same way for a pyramid. Now let's talk pyramids. So for a cone, it was volume equals 1/3 big B times h, where big B, like we've said a few times, is the area of the base. Pyramids are the exact same. Volume of a pyramid is 1/3 big B times h. Now your pyramids can be square pyramids, triangular pyramids, pentagonal pyramids, etc., etc. That's why we just do big B, because whatever the shape of your base is, that's what you need to find the area of. Now if I compared this, just like with the cylinder and the cone on the last slide, if I compared, let's see what I can do. Let's try this. If I compared, for instance, the square pyramid, that's not right. Erase a little bit. I'm not the best at drawing these things, and I get really nervous when I have to. Let's see. Not bad. Let me see if I can fix this one right here. So if I draw a square prism to sort of encompass this pyramid, I can see my back corner is a little off, but we're not going to fix that. That's a little off. If I encompass this square pyramid into a square prism, I am actually taking up 1/3 of the space of the prism with the pyramid's volume. Same with the cylinder. We had a cylinder drawn on our last slide, and I had a cone, and you remember the volume in the cone only filled up 1/3 of the volume of the cylinder, and it had the same radius and the same height. The same stands true for the square pyramid and the square prism. So that's why the volume of a pyramid is 1/3 of your base times of your big B times your height, 1/3 of area of your base times your height, because it's compared to the square prism, where volume of your prism, square prism, is area of your base, which in this case is B times B times height. So the volume of the pyramid is 1/3 of that. All right, let's get into a little discussion now. Those pictures we'll get to in a second. So to get into our sort of discussion, we're pretty okay with the area of a triangle is 1/2 base times height, because it's a half of a rectangle or half of a quadrilateral. We're okay with that. What we get confused with is the whole 1/3 when we talk about volume of cones or volume of pyramids. Where does this 1/3 come from? And I showed you a little bit with the cylinder and the cone. Pyramid was a little harder for me to show you, but I can do it with those really cool pictures over there. My question is, can we fit 3 congruent pyramids or cones can we fit 3 congruent pyramids or cones to form a prism or a cylinder? Now, if we just wanted to like pour water from one into the other, it's a lot easier to figure out. But when we're trying to physically fit together the shape, like we did with the area of the triangle, where we just pieced 2 triangles together, we can't physically shove 3 pyramids together to form to form 1 prism, right? It's really hard to do. So here, let's do this. I have 1 square pyramid, and it's fitting in the bottom of a prism. Now I've got 2 more square pyramids, and I'm trying to fit them into a square prism so that it fills it up. I can't do it. Okay, it just doesn't work. I can't fit 3 congruent pyramids or cones together to form a prism or a cylinder, and that's okay. How many total pyramids would I need to fit together to form a cube? And that's what we have right up here. I've got 1, 2, 3, 4, 5, 6 pyramids that I can fold all up and put inside this cone, which you see right here. I've got the yellow, green, orange, and pink. I'm missing the bottom blue, and there's the top blue. So I can fit 6 pyramids together into a cone. But what we see here is the height of the pyramid, that you can't see that, is just half the height of the prism. Okay, maybe we can see it a little bit better over here. It's going to be half the height of the prism. If I come down here to these pictures, maybe we can see it better. This pyramid right here is only half the height of the prism. The height here, this height versus that height. So if you look at the pictures down below, I fit 3 of them together, and it doesn't fill up the prism. But if I put in 3 more, like we have up here, 1, 2, 3, 4, 5, 6, I fold them all up and I fill them into this prism. I've got 6 pyramids in the prism, but they're twice the height of the cone. So to do just the height of the pyramid, I need half the height of the cone. Even though they don't fit in perfectly, the congruent pyramids don't fit into half the height of the cone. It's there. We've got empty space and full space. So if we poured liquid from the pyramids into the prisms, it would fill up exactly half. So 3 pyramids are half of a prism. No, 3 pyramids are a prism the same height as the pyramid. 6 pyramids are a prism 2 times the height of the pyramid. So that's why we do 1/3. Oh, for goodness sakes. 1/3 big B times H, because I've got 3 pyramids that fit into the prism. Good job. Let's move on. All right, let's try some exercises and use what we've learned. So a cone fits inside of a cylinder so that their bases are the same and their heights are the same, as shown in the diagram. Calculate the volume that is inside the cylinder but outside of the cone. Give an exact answer. Okay, give an exact answer means don't round. If anything has pi in it, leave the pi in it. If anything has a square root in it, leave the square root. Let's look at the volume of the cylinder first, because that's probably the easier one to figure out. Volume of the cylinder is big B times H. Big B is the area of the base. The base is pi r squared times H. So we've got pi r squared times H. This gives me 5 squared is 25. 25 times 12, I can't do in my head. 300. So the volume of the cylinder is 300 pi. Now, the volume of the cone, we know is a third of the cylinder. So I can just do a third of 300 pi. So this is the volume of the cylinder. This is the volume of the cone. Now, the kicker says calculate the volume that is inside the cylinder. Check. But outside the cone. Well, this is inside the cone. So outside the cone would be the difference. You can do 300 pi minus 100 pi gives us 200 pi, which is the answer. Or, I don't know why I drew a C, the volume outside the cone. If 1/3 of it's inside, then 2/3 are outside. Two different ways to get the same answer. Cool. A square pyramid has a volume of 245 inches cubed. Oh, I didn't put units on that last one. Sorry. Square pyramid. The height of the pyramid is 15 inches. What is the area of the base of the pyramid? And then what is the length of one side of the base? Okay, so our equation is volume is for a square pyramid, 1/3 big B times H, where big B equals the area of the base. And if the base is a square, it's B times B. If we know that the volume is 245, we don't know what B times B is. We don't know what the area of the base is, but we know the height. So let's go ahead and solve this. 245 divide by 1/3 and divide by 15. I got big B is 49. Big B is little b times little b, so b squared is 49. So one side of the base, one side of the square base, sorry, is 7 inches. So we have a square pyramid. We've got 7 times 7 times my height is 15. This was one question it asked for. And then, area of the base was the other one. So this would be inches squared, and that would just be inches. Big B was the area of the base, which is right there. And then one side is 7. Right, use the diagram below to answer the questions that follow. There's a few questions here, but one diagram. Determine the volume of the cone shown below. Give an exact answer, so don't round anything. Volume is 1/3 big B times H, where big B is the area of the base, which is a circle, even though it's not sitting on the circle. Pi r squared. If we look, we don't know the radius, but it's a right angle. I've got 11, square root of 137. I can figure out my radius. 11 squared plus r squared equals square root of 137 squared. 121. 137. 137 minus 121 is 16. So r equals 4. Pi r squared times the height. So 1/3 times 16 times 11 is 58 2/3 pi. If you've typed it into your calculator, you can hit that math frac button. Oh, for goodness sake, sorry. And you get 176 over 3, or 58 2/3. Either one works. But when it says give an exact answer, you would lose some credit if you gave me 0.6666, round it to 7, right? Okay, find the dimensions of a cone that is similar to the one given above on the previous slide. Explain how you found your answers. Well, what dimensions did we use to calculate the volume of the cone? We have 1/3 pi r squared times h. If we look at the two dimensions that we use to calculate the volume and mess with those, we would keep the same volume as we change the dimensions. So if I just look at like radius and height, I need a different radius. Let's see, what could I use? Let's do 12. Which height would correspond to that? Let's see, I have 4x equals 11 times 12. Divide both sides by 4. So that is the, let's see, that's going to be the height. I should have used h. And 12 is going to be the radius. Let's try it. Volume equals 1/3 pi r squared h. Remember, similar, they just have to have similar ratios of dimensions, and we would get a volume of a cone that's similar. So I'm going to do 1/3 times 12 squared times 33. It's going to be much bigger. 1584 pi is my volume. Now let's do a little test. I know it's not in the lesson, but if I do volume over volume, let's do volume of big over volume of little. 1584 pi, and the volume of the little one, I went back and looked, was 176 over 3 pi. If I do that division, I get 27. But my ratio is cubed. So if I take the cube root of both sides, my scaling factor is 3, which if I look here, my scaling factor was 3. So it totally makes sense. It should be times 3, not x equals 3. Sorry. Times 3. So 4 times 3 is 12, 11 times 3 is 33. So it works. Cool. Alright, these are sort of fun. Gold has a density of 19.32 grams per centimeters. Density equals 19.32 grams per centimeter cubed. If a square pyramid has a base edge length of 5, and it's square, that means all of them are, in my awesome pyramids, and a height of 6. Let's get a different color. And a mass of 942 grams. Is the pyramid, in fact, solid gold? If not, what reasons could explain why it is not? Recall that the density can be calculated with the formula density equals mass over volume. So let's figure out our volume of this. We know the mass, we don't know the volume. So if we want to do density of this pyramid, we need volume. So 1/3 area of the base, 5 times 5 times height. So 1/3 times 25 times 6 gives me 50. So volume equals 50 centimeters cubed. Density equals 942 grams over 50 centimeters cubed. 942 divided by 50 equals 18.84 grams per centimeters cubed. So that's the density of this particular square pyramid. So since the density is not the same as the density of gold, the pyramid is not solid gold. It could be because it's hollow, it could be because it's mixed with another metal to make it less expensive. It could be any reason, really. That's it for today. Yeah, I'll see you tomorrow.